Hello everybody, welcome back to another logic video. So today I'm going to walk us through the long and short truth table methods for analyzing some argument forms for validity. Now I'm going to, in some sense, give the game away. Today we're going to take a look at 4 argument forms, all of which are valid. These are popular argument forms, so originally we were going to get to the 7th and 8th chapters in the formal logic primer. The 7th chapter contains a list of popular, you don't have this, so I'm just telling you what's in there that you would have been getting. A list of popular valid argument forms as well as a couple of common invalid argument forms. So maybe next time we'll take a look at those invalid ones. So we're going to look at 4 valid argument forms that can be used in actual argumentation. So when you're looking around for this last homework assignment, there are decent odds that you will actually find something that has one of these argument forms. And you might not even realize that these are deductive argument forms. And so I figured by going through these today, we're going to do 2 things. One, help show you some popular argument forms. So as you're looking around for things or thinking about how to interpret something you've already found, these might be very handy. We're also going to see how to use both the long and short truth table techniques. So just more examples of that. I think there's probably going to be overlap with some of what I've already done. And like I just said, these are popular argument forms. So in fact, often when you're dealing with deductive arguments, you're often dealing with arguments that wind up having at least some of these forms in their components. So I've come up with 4 examples. The weather's a little bit crummy today. It's snowing again and got cool. So unfortunately, my lack of creativity has resulted in a lot of arguments that deal with the fact that it's snowing and what I'm doing about it, namely not really going outside and so on. So forgive me if the examples are a little bit boring or kind of everyday. I'm picking examples like that in part just to help highlight the structural features of what's going on here in the deductive arguments, rather than, in some sense, distracting us and getting caught up with some sort of controversial topic or some sort of confusing example or something like that. So the first argument form we're looking at, the Latin for it is Modus Ponens, which translates roughly into something like the way that affirms. You already use this argument form. I use this argument form. We find it all over the place. Odds are there's going to be a lot of this argument form contained in the homework assignments that you're doing. So look, here's the argument. If it's snowing, then it's cold outside. It is snowing, so it's cold outside. Now, there's an interesting question here about whether or not really these premises are always true, but we have that issue of assessing the premises for truth is something separate from the validity of the argument. Remember, keep that in mind. Whether or not an argument is valid really is a question about whether or not it has a truth-preserving structure. If its premises were all true, would the conclusion have to be true as well? Modus Ponens, the way that affirms, has a valid argument structure, and we'll see why that is with the truth table. So look, here we've got 2 simple statements in this argument. So we've got the natural language argument first, that's what's centered. Here's my translation. P, it is snowing. Q, it is cold outside. And just for fun, why don't we make S for snowing and C for cold? So I'm going to have to revise what the argument looks like, but it's just going to look like this. So if it is snowing, then it's cold outside. It is snowing, so it's cold outside. So we're going to make a long truth table first. And as a matter of fact, you've already seen this truth table. You've seen it several times, because all we actually need here is the truth table for an implication statement. That's really all we have here. We just have an implication statement with the antecedent being affirmed. That's really all that's going on in this case. Oh, and see, I've already defaulted to using P and Q instead of S and C, as I just decided to change it on the fly. And again, the statement letters, it doesn't really matter what letter you use to represent what statement. If using letters that help you remember that a particular statement means something, great, use that. If not, you can use A, B, C, D, you can use P, Q, R, S. It doesn't matter. You can use really whatever letters you like. Just make sure that one letter is always assigned to one simple statement when you're dealing with some particular argument. So this one simple statement should never have more than one letter when you're analyzing a particular argument. One simple statement shouldn't have more than one letter that it's represented by, and one letter shouldn't represent more than one simple statement. So I put together my header row here. We've got our two simple statements, S and C. We've got a complex statement, if S then C. We've got premise 1 and 2 identified, as well as the conclusion. Now we just have to fill in the truth values for the simple statements first. So given that we only have 2, it's the usual pattern. The left column, true, true, false, false. Next column over, true, false, true, false. Then in this last column, we've got just the implication statement truth table. So true, false, true, true. Because of course the implication statement's only false when the antecedent is true and the consequent is false. And so what do we have going on here? Well, this valid argument form, this modus ponens, really what's going on is that we have the first row in the truth table. That's really what this argument form is. It's just that row. What we have is premise 1 is an implication statement. Right? Premise 1 is saying it's true that if S is true, then C is true. If it's snowing, then it's cold. Premise 2 is saying it really is snowing, which right now it actually is. Conclusion, so it's cold. It's cold outside, right? That's what we have represented on this first row of the truth table. Now, as I was saying, whether or not the premises really are true is something that we can think about separately from the question about whether or not the argument is valid. So look, the implication statement, if it's snowing, then it's cold outside. Is that really true? Well, I can think back to maybe last summer, but certainly a few years ago. I remember I believe it was June, and it hailed here in Lethbridge. Presumably, hail is really a kind of snow, and it wasn't particularly cold, but it hailed. Now, of course, there's a question there. Where does it need to be cold for it to snow? It could have been cold up in the clouds, but not down near the ground where I was. So there's some interesting questions we can have about whether or not these statements are really true. But whether or not the premises are true, right? Whether or not the implication statement is true as a matter of how our world works, whether or not it really is snowing right now. I'm saying it is as I'm making the video, but you know, maybe I'm lying to you, or maybe by the time you watch the video, it's no longer snowing or something. We can debate whether or not the premises are true. And in fact, that can be a useful function of dealing with deductive arguments. It helps then focus the disagreement and the debate down to questions about whether or not the premises really are true. But in terms of the structure of the argument, we can look at this one, and in fact, it's a valid argument. It's truth preserving, right? If those premises are both true, the conclusion will have to be true as well. Now that we've done the long truth table, let's go ahead and make a short truth table for it. Now remember, the short truth table differs from the long truth table. We still make our header row in the same kind of way. So we put in our various statements. We label our premises and conclusion in the header row. So we do all the normal things we would do in the header row. But then we only construct one row under it. Right? Now in this case, we've got the conclusion. We try to set that to false. This is really what we're doing in the header row. We set it to false. We try to make all the premises true, and we work in an increasing order of complexity in dealing with the premises. So we've got just 2 premises here. The first thing we're supposed to try to do in the short truth table method is set premises that are simple statements to true. So in that case, this is premise 2 here, just the statement S that it's really snowing. Now, if it is actually snowing, right, if that's true, but it's not actually cold outside, then if you just think about it in normal terms, it would have to follow it's just not the case that if it's snowing, then it must, absolutely must be cold outside, right? That turns out to be a false statement. So when we think back to my experience with that June and it was hailing, well, it was warm as far as I was concerned, and it was snowing, if hail in fact is a kind of snow. So it was just false that for it to be snowing, it had to be cold outside. In fact, it can snow when it's warm outside, apparently, right? So what we have in this row here, so you know, that's just a way of talking through it. But what does this row on the short truth table show us? It actually shows us that the argument is valid, right? What did we do in the short table? Well, we are actually forced to construct, if we look back up, we're actually forced to construct the second row on the long table. Why? Because we set the conclusion to false, right? The conclusion was C, that it's cold outside. We just, in the short truth table, we're trying to show invalidity by making the conclusion false and all the premises true. So we started by making the conclusion false. We then set the first premise to true. And then, well, what did that leave us? Well, if we look up here, if we look on the long truth table, in the second row of that truth table, this is what we have. S is true, well, C is false. And in that situation, what do we have? We have the implication statement, if S then C, winds up being false as well. So we've just reproduced that second row here. In our quest to show that the argument was invalid by making the conclusion false while the premises were true, we failed. We couldn't do it without contradicting ourselves. We had to admit at least one premise was false when the conclusion was false. But what does that tell us? It tells us that this argument form is valid. Okay, let's move on to the next argument form. Modus tollens, or the way that denies. This is quite similar to modus ponens. It involves an implication statement, but works the other way around. So in a modus ponens argument, in a way that affirms, we have an implication statement, right? If this, then that. We affirm the antecedent, and so we get to affirm the consequent as well, because we know if the first thing's true, the second thing has to be true. We get a similar thing here. We say, look, if one thing's true, something else must be true. But we realize that the second thing, the consequent, isn't true, that it winds up being false. And if the consequent is false, that means the antecedent must be false as well. We'll see that on the truth table. So look, here's my natural language argument. If it's sunny, then I'll go for a walk. I'm not going for a walk, so it's not sunny. So I've got here, I'll go ahead and do S and W, sunny and walk, right? If it's sunny, then I'm going for a walk, but I'm not going for a walk, so the conclusion is that it's not sunny out. Now here again, we will make our truth table. We've got S, we've got W, we've got if S then W. Now in this case, I've made 3 columns because we've just got 2 simple statements, and then we've also got an implication statement, but we also have 2 negations. And remember, we want to make columns for our negations as well, because whether or not a negation is true or false depends on whether or not what it's negating is true or false. So a little bit more work here. This time we've got 5 columns instead of just 3. So of course I've made my header row again, labeled the conclusion, 2 premises. Now I've got 2 columns for the simple statements. They're neither premises nor conclusions, but of course I need those columns to help tell me about whether or not all of these other complex statements are true or false. Because whether or not a complex statement is true or false depends on whether or not the parts that make it up are true or false. And ultimately, all of this always comes back to the simple statements, right? Any complex statement, whether or not it's true or false, will ultimately depend on some combination of the truth values of simple statements. So we've got T6, that doesn't make sense. We've got our normal true, true, false, false, true, false, true, false for the simple statements, right? Simple statements always work the same way. If you've got 4 rows, you have this pattern. If you have 8 rows, you're going to have the normal 8-row pattern, and so on. Now, when we come around to our negations, we just reverse the truth values. So whenever S is true, not S is false, and vice versa. So for S, we had true, true, false, false. So over here, we have false, false, true, true. For W, we had true, false, so we have false, true, false, true. Lastly, for premise 1, the implication statement, if S then W, if it's sunny, then I'm going for a walk. Whether or not that implication statement is true depends on the truth values of S and W again, right? So we have to, in some sense, ignore, I'll just get rid of them for the moment. We have to, in some sense, ignore those columns, because really what we're interested in are what's going on in the simple statement columns and what's going on over here in the implication statement column. So as with the truth table above, we've got true, false, true, true, because the only time if S then W is false is when S is true but W is false. So there, we've got this all set up. So what are we looking for this time? Well, like I said above, really what we have on this long truth table, somewhere or other, we've got the argument form we're looking for. So we've got if S then W, right? Premise 1 is saying that that's true. So that could be row 1, 3, or 4. In rows 1, 3, and 4, S is true. So maybe I'll fill those in. I hope the visuals are helping here rather than doing the opposite. So look, if I'm just sort of trying to figure out what row on my long table represents this argument form, well, I need to find where if S then W is true, and I get that on these 3 rows. I also need, because premise 2 tells me not W is true, right? It's true that W is false. Where do I get that? I get that in rows 2 and row 4. Now, what else am I trying to look for? The conclusion is not S. Where do I get that? Well, in row 2, the conclusion not S is false. So that's not the one I'm looking for. But in row 4, I get not S. So row 4 is actually exactly what I'm looking for, right? Premise 1 tells me if it's sunny, and we can go back to the natural language here. If it's sunny, then I'll go for a walk, right? Premise 1 is telling it, it's saying that's true. Premise 2 is saying, I'm not going for a walk. Carl is not going for a walk right now, right? Not W is true. I'm sitting here making this video. If I'm sitting here making the video, I'm not going for a walk. So if it's true that if it were sunny, I'd be going for a walk, and it's also true that I'm not going for a walk, then it must be the case that it's not sunny out. And that's exactly what we see in row 4 here. So here again, we've got a valid argument for. Right? We can find that here. Now, let's go ahead and make the short truth table. Remember, we're going to need the same number of columns as we do up here. We need the same header row. Just sticking that together here. Center that. Give it some nice shading. Now, what we're trying to do with the short truth table is really create an instance of invalidity if we can. So we set our conclusion to false. That's how we start. And of course, as soon as we have enough information to fill in another truth value, we do. So if we know not S is false, that tells us S is true. Now, what else do we need to do? Well, we need to try to make both premises true. We should do that in increasing order of complexity. We start with simple statements. But we don't have any simple statements acting as premises in this argument. The next best thing is a negated simple statement, not W. Let's make that true. Because if we know not W is true, that means we know W is false. We have information we can fill in when we know a negated simple statement is true. So now we only have one cell left. If S then W, right? Can we say that's true without contradicting ourselves? Well, not if S is true while W is false. And that's exactly what we have in our truth values for S and W. When we started by making the conclusion false, not S, that told us S has to be true, right? S has to be true if not S is false. Otherwise, we've contradicted ourselves. We need the premise 2, not W. That has to be true. If not W is true, then W is false. To say otherwise would be to contradict ourselves. Now we're in a situation where we're wondering if S is true, does that mean W has to be true as well? Well, not if S is true and W is false. To say if S is true, W must be true at a time when S is true but W is false would be to contradict ourselves. So we have to admit premise 1 is false. To say that it's true would just be to contradict the other truth values we've already put in this row. So we were unable to construct a row here that shows us that the argument is invalid. And here again, if we look up on the previous table, we'll see that we've actually constructed, this time, row 2, right? We've got the same thing. The conclusion is false, premise 2 is true, premise 1 is false. We ended up constructing row 2 when we were trying to use the short truth table method. Now, I'm just showing you that in terms of that we made one of the rows that shows up on the long truth table here. I'm just showing that because I talked about that last time, that when we're doing the short truth table method, ultimately what we do is end up constructing a row that would be on the long truth table anyway. Now, depending on how you fill in the truth values and the order in which you go about doing it, you might wind up constructing different rows from the long truth table. Long truth table has all the possible combinations. So any row we construct in the short truth table, as long as we don't make a mistake, whatever row we make or set of rows we make would be rows that showed up on the long table anyway. We're using the short method just because it's quicker to make one or maybe two or three or four different rows, depending on how many ways the conclusion could be false. It's much easier to do that than go through and have to actually construct the full truth table. But to really understand what we're trying to do with the short truth table technique, it's very useful to already know the long truth table technique, to know why we're filling in values in a certain sort of way and what it is exactly that we're looking for. Now, just taking a quick look back at the long truth table, just to sort of make it clear exactly what's going on here. So I said what this argument really shows us is we capture that in line 4. Because in line 4, both premises are true and the conclusion is true. Now, of course, the long truth table shows us that the argument is valid if we look in the rows where the conclusion is false. If we look there, that's really rows 1 and 2. In each of those rows, we see that at least one premise is false. So in the long table, we see that every time the conclusion is false, in each of the 2 scenarios, one of the premises turns out to be false as well. That shows us the argument's valid. In the short truth table, we have the conclusion being false, but we were forced to admit that at least one of the premises had to be false as well, right? And hopefully by putting it this way, you can see that really what we did in the short table is just reconstruct row 2, right? Now, if we had filled in the values differently, so here I'm just going to copy and paste my short table. This is for illustrative purposes only. If we had filled in our table differently, we approached it differently. So we still start by making our conclusion false. Of course, if not S is false, S is true. Say, instead of starting with premise 2, because it's a negated simple statement, we started by making that premise true because in that sequence I gave you, that order to set premises to true, I said, do that, start with simple statements, then do negated simple statements, and then conjunctions, and then, right? What if we just tried making premise 1 true first instead, right? So instead of starting with premise 2 as you should, what if we started with premise 1? And note that sequence I gave you, that order to approach premises in when you're trying to make them true, you don't absolutely have to do that, right? That's just a helpful way of doing it. If you do it that way, you're going to cut down on the number of potential instances you have for making an error or something like that. But there's nothing exactly wrong with doing it this way. So let's say we did premise 1 first. We set it to true. So in our conclusion is false, we say, but premise 1 is true. Premise 1 is if S, then W. If it's sunny, then I'm going for a walk. We already know S is true, right? Why? Because we made the conclusion false. That's just how we start one of these things. So if S, then W is true, and we know S is true, then W must be true as well, right? We just have to get that. And you can actually see that up on the first row of the long table, where if S, then W is true, and S is true, then W must be true, right? That's the only place, and I'll just go ahead and stick that in green. On that long truth table, that's the only row where you have if S, then W is true, and S is true, right? Because here in rows 3 and 4, where if S, then W is true, S is false. So if we already know that if S, then W is true, and we know that S is true, then we know we're putting together this first row. And in that first row, W is true. So we can fill that in here. Right? So if we filled in premise 1 is true, and we know our conclusion is false, then we know we have to make W true as well. So if we know that W is true, let's go look at our second premise now. What about not W? Well, as soon as we know W is true, we know not W is false. And what does that mean? That means even if we went about doing the short truth table out of order, so to speak, we did it in a different order than I recommend in the text, we would wind up still showing that this argument is valid because we just cannot make both of those premises true. Well, the conclusion is false without contradicting ourselves. Okay, so that shows us modus tollens, this other common argument form. Modus tollens really says if one thing is true, then something else must be true, but this other thing is false, so the first thing must be false, right? If it's sunny, then Carl's going to go for a walk, but Carl's not going for a walk, so it must not be sunny. Because if it were sunny, he would definitely go, but he's not going, so it's not sunny. Right? Back up to modus ponens, right? If it's snowing, then it's cold, right? So if it is snowing, and we know that, then we know it must be cold, right? Maybe you don't know it's cold already. You just sort of look out the window and you say, I wonder what the temperature is like outside. And then you see a bunch of snow and you go, oh, okay, well, I guess it must be cold then, because if it's snowing, it must be cold. We use this kind of reasoning all the time. We use this reasoning when we're thinking about rules. We use this reasoning when we're thinking about causation, right? We think about one thing causing something else to happen. We think about what happens, say, if you break a rule, do you deserve a certain kind of penalty or a fine or something, right? We think about these sorts of relationships all the time. And the implication statement helps model that. And these two common valid argument forms let us, in some sense, use an implication statement two ways. We know that if one thing's true, something else must be true. We can use that if we know the first thing is true, or if we know the second thing is false. That lets us know something about what's going on the other side of the implication statement. Okay, disjunctive syllogism. So we have the disjunction, right? The or, either this or that. A disjunctive syllogism is where we have an either or statement, right? This thing's true or that thing's true. And we know one of the things is false. So look, I made this one up. I certainly hope the premises are true in this one. Either my logic videos are helpful or I'm wasting my time. I'm not wasting my time, I hope. So these logic videos are helpful. So what's my translation there? Well, Carl's logic videos are helpful. Q, right? Carl is wasting his time, right? Hopefully not. So if I symbolize the argument, right, I show how these simple statements fit together, how these turn into premises and a conclusion. If we look at the natural language, we get it represented this way. The first sentence is really the first premise, either P or Q, either Carl's logic videos are helpful or Carl is wasting his time. The second sentence, the first clause is really premise 2, right? It's not true that Carl is wasting his time, right? I'm not wasting my time. Conclusion, so these logic videos are helpful, right? I'm just going to leave these as P and Q this time. We could make them something else, right? V for video, W for wasting time, whatever. I'm just going to leave those P and Q. Here again, we'll start with the long table. This time, we're going to actually need 4 columns because we have 2 simple statements. So there's 2 columns. We have a negated simple statement, right? Not Q. There's another one. And then we've got the, I don't know why I'm doing this instead of this, whatever. And we've got our disjunction, P or Q. So we need 4 columns. We've only got 2 simple statements, so that's 4 rows in addition to the header row. So here again, let's just stick this together. Oh, what did I do? All right, so we've got P, we've got Q, we've got not Q, we've got P or Q. Oh, and one quick note, sometimes I put a space between the operator and what it's operating on. Sometimes I don't. It doesn't really matter. Whether or not there's a space there is a little bit of a stylistic question. If you put a space there or don't put a space there, that's not going to change whether or not you're right or wrong. The use of brackets can be important, and in my next video, we'll deal with some arguments that have brackets in them again. So this video doesn't really have any brackets, just to try to keep things fairly accessible and showing how the long and the short truth table methods overlap in a certain kind of way, showing you these common valid argument forms. That's really the point here. Next time, I'll try to make things a little bit more complex, deal with some complex statements that require brackets for their proper syntactical expression. So we've got our first premise, our second premise, and of course our conclusion. Our conclusion is actually just P, right? It's just one of the simple statements this time. So go ahead, I'm going to center all that, give this a little bit of shading. Is there a different color? Let's try a little purple. Oh, that's a very dark purple. Can I make a lighter purple? I don't know. I'm not, why don't we go with that? Whatever that color is, sure. I'm not a color person, in case you didn't pick that up from my almost exclusively black and white slides. I also realize it's not that I have anything against colors. I just don't have very good taste when it comes to the use of colors, which is part of why I tend to avoid them and sort of visual imagery war generally. Honestly, my fear is to be more distracting with things like images than anything else, which is part of why I shy away from them. So maybe if you think I should use more images and more sort of coloring and things like that in my presentations, hey, why don't you tell me in a course evaluation? That would be a really good place to tell me that and why it would be a really good idea. Okay, so we've got our long truth table set up here. Here again, we've just filled in our simple statement values in the normal way. It doesn't matter that our conclusion is a simple statement, right? The truth values in the rows are just always the same for simple statements. We've just reversed the truth values from Q for not Q. A disjunction is true. P or Q is true as long as either or both of them are true, right? So we only have this one instance where it's false in the last row. And what do we have here, right? So either Carl's logic videos are helpful or he's wasting his time, right? So in that first premise, we said that this statement is true, right? P or Q is true. That's what the first statement is. So we know we're looking at one of these three rows. That's really what we're picking out here. Premise 1 has said that P or Q is true. So we know it's not row 4 we're looking at. Premise 2 says that not Q is true. Not Q is true. Where do we find that? We only find that in rows 2 and 4. Now, we already know we're not looking at row 4 because that wasn't a row where the first premise was true. So the only row we're constructing here is row 2. That's the only row where premise 1 and premise 2 are both true at the same time. And in that row, if we look for the conclusion, if we look for P, what do we see? In row 2, P is also true. So this argument really picks out this second row. Right? It's telling us, if you have this true implication statement and you know one part of it is false, then you know that the other part's going to be false as well. I want to quick copy and paste this because even though I did P or Q here and then I did not Q, this argument form works the same way if we were to switch these around. What do I mean by that? Instead of not Q, if we have not P, you can conclude Q. Why is that? Well, let me show you. It's going to take a moment. We got to change this to not P. We're going to have this, 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 right? So I've changed the argument from saying not Q and concluding P to saying not P and concluding Q. Really, what a disjunctive syllogism does, it says here's two things. One of these two things is true, and it's telling you one of them is false, and then concluding the other thing must be true on that basis. Right? So we have P or Q. If Q is false, P must be true, or if P is false, Q must be true. So I've changed the not Q column from the original form here to be the not P column. And if we just go through and look again, which row are we trying to construct? Well, if we know that P or Q is true, you know, it's one of these three rows. We also know that not, oh, I messed that up a little bit, sorry. If we know that not P is also true, well, that's only in these rows 3 and 4. So given that we know both premises are true, turns out all that we are, all that we are constructing here, really, what our argument is actually this third row this time. So in the first instance, we were picking out the second row of that table. This time we're picking out the third row. When both premises are true, and we only get that in this one row here, then the conclusion must be true as well. And we can do this. So I hope that makes sense. I hope I didn't go too quickly. All I was trying to do is show that when you have a disjunctive syllogism, it doesn't matter which disjunct is false. you can still conclude that the other disjunct is true. So you got a disjunction, either this is true or that is true. You say one of them is false, so you can conclude the other one is true. Right? Let's go back to the original example. So I'm just going to get rid of the other one. And we'll make a short truth table just to show us that what we were doing works there as well. So if we've got the short table, we got, and we'll just stick with the original version of this that we did. So we've got P or Q. We've got not Q. We've got P. We'll go ahead and, oh, why don't we do that color? That's kind of a purple this time. Why not? So if we're doing the short table, we know we start by making our conclusion false. And then what do we try to do? Try to make both premises true. Start with any simple statements. We don't have any of those. We move on to negated simple statements. We've got one of those in P2. So if we know P2 is true, we're trying to make all the premises true. That tells us Q is false. Right? Whenever not Q is true, Q is false. Now we go to our last premise, P or Q. P or Q is true so long as either P or Q or both of them is true. Do we have that? Oh, no. Right? Both P and Q are false. When both P and Q are false, P or Q is false too. So here we go. We started by making the conclusion false. We tried to make both premises true, and we just couldn't do it. On pain of contradiction. If I had said P or Q is true after I said that P is false and Q is false, I would just be contradicting myself at this point. And here again, the row we constructed turns out to be a row on the long table, right? We just constructed row 4, and this time here, I'll highlight both of these in, I don't know, yellow, right? Look, we have the same row. We ended up making row 4 on our short truth table. And just as we did above, we could, I'm not going to do it here, if we had filled in the truth values differently, if we had started by making P1 true, and then tried to move on to P2, we would have just constructed a different row on the table. We would have ended up, in this case, constructing row 3 on the long table. So see if you can make sense of that, just sort of looking at what I've done here. Okay, so we've now looked at 3 common valid argument forms. We've got the way that affirms, the way that denies. We have the disjunctive syllogism. This is another common argument form, right? People are saying, look, one of 2 things is true. Either this thing is true or that thing is true. And it's not one of them. So it must be the other one. That's another valid deductive argument form that we use all the time, right? Just think about it. Oh, where did I put my keys? Well, either I put them in the little key thing by the door, or I left them on my desk. I look at the little key thing at the door. Oh, they're not there. So they must be on my desk, right? And it's true that they will be on my desk so long as it was true initially that either it's in one of, my keys are in one of those 2 places, right? If that's my initial premise, right, my keys are either by the door or on my desk. If that's true, and I look by the door and they're not by the door, then they must be on my desk, right? If they aren't on my desk when I go to look, then when I think back, I have to say, well, it was actually false that either my keys were by the door or on my desk. Turns out they could have been somewhere else because they really are, right? But this is how we reason. We go from what we think is true, right? We then get more information, we pull that information together and draw some kind of conclusion from it. Okay. Now, the last, I need to get rid of a bit of the spacing here just to not have everything going on to different pages. Now let's look at this last valid argument form, the hypothetical syllogism, or it's often called a chain argument. This is one that links together multiple implication statements. And so just as a matter of fact, when you're looking at deductive arguments, almost all deductive arguments, if it's really an argument worth making, is going to make use of a disjunction or an implication statement, almost certainly. And it's probably going to use one of the forms we're looking at here to, in a sense, move the argument forward. So when we're thinking about negations and thinking about conjunctions, those are really ways of helping to express certain complex statements, modify different elements of an argument, but we're really thinking about acts of reasoning. Typically, we're using implications or disjunctions to do it. Okay, here's my natural language argument. And apologies for basically just repeating what I was doing above. It's a little bit different this time. If it's snowing, then it's cold outside. If it's cold outside, then I'm staying home. So if it's snowing, then I'm staying home. So I've got a translation into P, Q, and R. This time we've got 3 values, right? It is snowing. It is cold outside. Carl is staying home. And that really captures what's going on. If we look at the symbolic representation of the argument down here, right? If it is snowing, then it is cold outside. If it is cold outside, then Carl is staying home. So if it is snowing, then Carl is staying home. The conclusion of this argument is another implication statement. The whole point of this argument is just to show that there's this complex pattern that exists, that, you know, this thing leads to that thing and that thing leads to this other thing. So if we start here, we're going to end up over there. Right? So now to make this one a long truth table, this is going to take some more work. Right? Now we have 3 simple statements. So we know we're going to need 8 rows in addition to the header row. So we're thinking about columns. We have 3 simple statements we have to put in there. And then we have 1, 2, 3 different implication statements. And then we're also going to need 8 rows in addition to the header row. So now I'm going to fill this in rather quickly. My apologies if it's a little too quick, but I hope part of what you're seeing here is that once you get some practice at this, you get the hang of it. It's not as cumbersome as it seems. Now, that said, in practice, are you going to be making a lot of truth tables when you're doing an argument? Not necessarily, but what doing them helps show us is just how the combinations of certain simple statements can add up to a lot of really complex information. And so if you deal with things in fairly simple terms, you can actually get some fairly complex results. You can account for a lot of complexity with some simple analysis. You know, going down to the basic constituent parts, right, are true and false simple statements. Either this statement is true or false, that statement is true or false, that statement is true or false, and then seeing how those combine to make more and more complicated things. And if you think about this in terms of, say, computers, you know, and maybe some of you are taking computer science or something like that, when it gets right down to it, all modern computing works this way, right? You've got some kind of circuit, it's on or it's off, right? If it's power or it doesn't, it's true or it's false. And on the basis of that, multiplied by millions of interconnections, you wind up getting all the sort of complexity we get from computers. One of the aims of neuroscience is trying to find how different sorts of connections in the brain, right? It's true or false that this is firing and that's firing, and if these 2 things are firing, something else is going on. Trying to find those sorts of relationships as well. All right, so I'm just quickly filling in all the values here, trying to keep the video to approximately 50 minutes, so my apologies for moving very quickly here. I just realized I made a mistake up there. See, it's still very easy to make a little mistake even when you know what you're doing. So try to pay the best attention you can. Okay, and here again, we've got implication statements. Given that all I'm dealing with are simple statements, right? It's for all 3 implication statements, they're just linking together 2 simple statements. I know a simple statement is only false 1 out of 4 times when dealing with a simple statement. So if I've got 8 rows, I know each of these will only be false twice, and they're only false when the antecedent is true and the consequent is false, which is exactly what I found here. So as I was mentioning before, you wind up finding patterns based on what's going on. Here I've got true, true, and then false, false, and then it's all true. And the next one is true, false, true, right? True, false, true, true. And that gets repeated, true, false, true, true. And the last one, true, false, and then it's all true, 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 true. And if you take the time, you can see what the pattern is back over in simple statements. We're not going to bother with that here. But what have we really done with our argument? Well, again, let's just pick out the row that this argument form actually corresponds to. So we know that if P and Q must be true, and we get that, so just going through them in terms of premise 1, premise 2, conclusion. We know premise 1 is true, so we've eliminated 2 rows. We know premise 2 is true, That's going to eliminate 2 more rows for us. We also know our conclusion is true. That's what the argument is claiming we see, right? So what do we have here? Well, if we look again at our long truth table, what's going on? This time, there's actually 4 different rows that are picked out on this truth table by this argument form. And remember, the implication statements are just telling us that if something's true, something else is going to be true. Nowhere in here have we actually been told that any of these statements are true, right? We haven't been told that it is snowing. We haven't been told that it's cold. We haven't been told that Carl's staying home. Our conclusion is just the implication or hypothetical statement that if it's snowing, then Carl is staying home. That's what the conclusion is. And we draw that conclusion on the basis of the premises we have. So if we look at the long truth table here, we actually get multiple situations where both premises are true and the conclusion is false. We get that in row 1, we get that in row 5, and we get that in rows 6 and 7, right? So what we've constructed here, we find on multiple rows on our long table. But in every one of those rows where both premises are true, the conclusion has to be true as well. And in fact, if we're just using the long truth table method to check for validity, every time that conclusion is false, it's only false in 2 rows, it's false in row 2 and row 4, we have a false premise in each of those rows as well. Right? So if we're using the long truth table method, we'd see this argument is valid based on row 2 and row 4. We just look at the argument structure we have, right? If premise 1 is true and premise 2 is true, that tells us that we're only looking at certain rows on the table where both those premises are true. And in every single one of those rows, the conclusion is true as well. So this is a valid argument. Now, and one thing I'll say, I know as I've been going through this video, I've been picking out the row we're constructing, which is something a little bit different from the normal check for validity, where you look where the conclusion's false and then see if all the premises are true. In some sense, these are 2 sides of the same coin. Now, still, when you're checking for validity, check the rows where the conclusion is false and see if all the premises are true. That's really the right way to go about it. But part of what I've been trying to do in this video is just show you how these valid argument forms really, what they're doing is picking out or reproducing certain rows on the truth table. Okay, let's do the short truth table technique and get everything we're just doing. So we'll try to duplicate what we're doing. So I just copy and pasted my header row this time just for the sake of simplicity. Now, this time things are a little bit more tricky. Our conclusion, if P then R, that needs to be false. Now, when is if P then R false? Only in the situation where P, the antecedent, is true and R, the consequent, is false. So I can fill in those values now because I know that when if P then R is false, then P is true and R is false. That's the only time that implication statement is false. Now let me try to make both premises true. They're both implication statements, so it doesn't really matter which order I try to set them to true as, right? It's not like I've got a simple statement or a negated simple statement or a conjunction or any of those other things that were easier to deal with. So let's deal with premise 1, if P then Q. Let's say that's true. Now I look over to the simple statement values that make up if P then Q. I know that P is true, right? I already had to establish that from the conclusion being false. So I know that P is true. Now I'm trying to say if P is true, then Q is true. So what does that tell me? It tells me Q has to be true. So I have to fill that in, right? I have to say, well, Q is true, right? Because what do we have here? We have a modus ponens on our hands. We have a way that affirms. I'm saying if P then Q is true. I'm also saying P is true. So what's the conclusion? Just if we took that as one act of reasoning, just pulling that together into a little argument all on its own, it would tell me that Q must be true as well. Now, I know that. I know Q is also true based on what I just did. So if I look at premise 2, if Q is true, then R is true. Can I say premise 2 is true without contradicting myself? Well, let's look at Q and R. Q is true and R is false. Now, if Q is true and R is false, it is just not the case that if Q is true, R must be true as well. So to be consistent, I need to say that P2 is false, right? If Q is true, R can still be false because that's what's happening in my row here. So the short method here, instead of having 8 different rows that we constructed and trying to check 2 different rows when the conclusion is false to see if at least one premise is false, we cut our work down for us, right? We said, okay, we know the conclusion's false. That's just what we're trying to make. We're trying to make a row where the conclusion's false and all the premises are true. Let's try to fill in all the premises and make them true without contradiction. And we just couldn't do it. What did we wind up doing? Well, we actually reconstructed, what was it, row 2 this time. We made row 2. And again, just for the sake of demonstration, right? We're done, a short table here. But let me just copy and paste it. Let's say instead we wanted to try to fill in the table in a different order. So we'd still always start with the conclusion being false. Because that conclusion, that implication statement is false, we know that we have to fill in P being true and R being false. Let's just reverse order. Let's make the second premise true this time. We'll start there. P2 is true. If Q is true, then R is true. R is false. If R is false, and the implication statement, if Q is true, then R is true, then Q must be false as well. And you can just look at the implication truth table to see that. Right? If we know that the consequent is false and we know there's an implication statement, we know that the antecedent is false as well. In fact, that's what Modus Ponens, the way that denies, that's what it showed us. If that seems a little bit unfamiliar, a little bit weird, go back earlier in this video and look when we were dealing with the second example. Okay, so from the fact that the second premise is true and that R is false, we know that Q is false. We filled in all the values for our simple statements this time. Now we just have the last premise to deal with, premise 1 in this case. If P is true, then Q is true. Right? And that's saying literally, if P is true, then Q absolutely 100% must be true. No ifs, ands, buts about it. What do we have on our hands? P is true, well, Q is false. Well, if P is true, well, Q is false. It's just not the case that when P is true, Q has to be true as well. So this time, premise 1 is going to be false. What did we make if we tried to fill in the premises this way? Well, we still showed that the argument is valid. Why? Because when the conclusion is false, at least one premise has to be false as well when we're being consistent. Right? We can't make a row where the conclusion is false while the premises are true. When we first tried it, when we did it the other way, what did we do? And I'll use a little bit of shading again just to help show this. When we did it this in the first short table, what did we wind up making? We wound up making the second row on the long truth table. Right? We've got the conclusion is false, premise 2 is false, premise 1 is true. When we did it this other way, when we approached filling in the premises in a different order, what did we actually wind up making? What do you know? We actually wound up making row 4 on our long truth table, which is another case where the conclusion is false. And it turns out you still can't have both premises be true there. So I hope this video has been helpful in showing how the short truth table method is really a way of constructing particular rows out of a long truth table. Ultimately, we get the same result. If the argument is valid, we see that it's valid. If the argument's invalid, we'll see that it's invalid. The short truth table is just a kind of shortcut method of getting to the rows we're really interested in on the long truth table. So that's one thing we've seen in this video. Another thing we've seen in this video are the 4 common valid argument forms: the way that affirms, or modus ponens; the way that denies, or modus tollens; the disjunctive syllogism, right? Either this or that, not that, so this; and the hypothetical syllogism or chain argument, right? If this, then that; if that, then something else. So we know if this, then something else is the case. So hopefully those common valid argument forms will make it a little bit easier when you're trying to pick out something for the homework assignment, or it'll help clear up some of your own thinking when you're trying to interpret how that argument is working. If you're already pretty sure you found a deductive argument, you're looking at it, thinking a little bit of, how does this really work? How should I think about this in terms of premises and conclusion and how the statements relate to each other? Often you will find these argument forms. So I hope this video has been helpful for showing you some of those argument forms. I also hope it's been helpful in showing you how the long and short truth table methods are in some sense complementary. They're really trying to do the same sort of thing. We're just going about it a little bit differently. I also hope I haven't made things more confusing by picking out the rows on the long truth tables that really show us the steps in the argument as we're getting. Really what I'm doing there is when we have an argument like this one, every time there's a premise being asserted, somebody's saying something is true. They're saying, in this case, this chain argument, if P then Q, they're saying it's true that if P is true, Q is true. Premise 2, they're saying it's true that if Q is true, then R is true. The conclusion is the assertion, so it's true that if P is true, then R is true. And we can try to pick that out on our truth table. Do we see instances where we get all that information, where we get those things all being true? We do. Do we ever find an instance where the conclusion, if P then R, could be false while both premises are true? No, we can't, right? We can't find that on the truth table. Anytime the conclusion is false, one of the premises must be false as well. What does that tell us? We have a formally valid argument on our hands. So we've got the makings of a good deductive argument. It has the right kind of structure. It's a truth-preserving structure. So as long as the premises are true, we know that the conclusion will have to be true as well. All right, I hope you're all doing well, and I'll see you in my next and final video, which I'll be putting up on Friday, and we'll deal with some more complex arguments that involve some brackets and using the short truth table method for trying to test them for validity. You might use the long truth table a little bit there, but I think mostly we'll focus on the short method because it's a more efficient way for dealing with a complex argument that has a lot of component parts to it. I hope you're all well. Bye for now.